So now this is our first lecture of VLSI design, and in VLSI design we will study the different techniques of VLSI design. We will study how we can design a system at different level of abstraction. We will design a system at the transistor level. We will design a system at the structure level. We will design a system at the gate level, and we will also design the system at a behavioral level. But before explaining all these level of abstraction, so first I have to ask a question that what is abstraction? I have already taught in embedded system course that what is abstraction? G. What is abstraction? Can you let me know that what is abstraction? Any beta? Anybody? What is abstraction? Anybody?
Sir, we have studied abstraction in C++. Can I tell you
Hmm?
that concept? There it is
What is it?
when there is a user interface such that so जैसे cars में होता है कि there is a lot inside the engine and everything, मगर
Very
ड्राइवर
good.
के लिए सिंपल वो स्टीयरिंग वगैरह सिर्फ उसे उसका नो हाउ आना चाहिए, बाकी he doesn't need to know all the difficult mechanical concepts behind making the engine and everything. That's an example of
Very good.
abstraction.
Very good. Very good. So if we have this defined abstraction, so we define abstraction as to hide the internal details of the system from the user. So what we do in abstraction, what is the basic advantage of abstraction? The basic, the primary advantage of abstraction is that we hide the internal detail of the system from the user. Okay, so how the user can interact with the system? How the user interact with the system? How the user interact with the system? The answer: interact with the system interfaces. So let's assume I already give an example of a car. So if we have a car, so in the car, what are the internal details of the car? What are the internal details of the cars? Engine,
Yes, sir. Braking system,
braking
suspension.
system, braking system. But the user does not know how the engine works, how the braking system works. So these are the internal details. So what are the interfaces for the car?
Steering
Sir,
wheel.
steering, yeah.
Yes,
Braking pedal, accelerator
steering
pedal.
wheel, and brake. For instance, these are the interfaces at the car with which you interface the car. So the basic advantage of abstract is to hide the internal details of the system, and user is interacting with the system through the interfaces. So now let's give another example of a computer. Okay, so inside the computer, what are the internal inside the computer? What are the inside the computer?
सर रैम हार्ड डिस्क वगैरह प्रोसेसर
Very good.
Processor,
So
yes.
into the internal of the system is RAM, hard disk,
प्रोसेसर
processor, memory. So how do you interface with the computer? How do you interface?
कीबोर्ड माउस स्क्रीन
So keyboard. So you interface with the system through the keyboard and mouse and screen and USB. There are also other interfaces with which you interact with the system. So actually, the internal details of the system get how your keyboard is interfaced with the CPU and how the data is communicated between the keyboard and your CPU, how the data is displayed on the screen. All these details are hidden from the users. You get my point or not?
Yes.
So very good. So now we will use we will study different type of domains. We will study different type of domains. So the first domain is the behavioral domain. So if you look at the left side, on the left hand side, can you see on the left hand side? The
Yes, sir.
behavioral domain. Okay. What is a behavioral domain? So this behavioral domain is typically used by software engineers. Okay. So this behavioral domain is typically used by the software engineer. And if we see at any code, okay. So on the top of the level there are application programs. What are the example of application programs? What are different application programs in your computer?
Sir, Microsoft Word,
Very
OneNote,
good. So, yes, very good.
Adobe
So
PDF,
actually,
Chrome.
if you say yes, so if we have applications, what are the applications? Excel, Outlook. These are different application programs. These are different applications that are on the. So these are different applications. Okay, what is an operating system? What is an operating system? What is the job of the operating system? Hmm? What is the job of operating system?
Yes, other
Sir,
interaction.
So operating system allocates the memory for the program. So what is the job of the operating system? I'm writing on the right hand side. So the operating system operating system provides an interface between application program. What is an application program, beta?
सर अभी आपने बताया एप्लीकेशंस जितनी भी सारी होंगी.
Any application, Microsoft Word, Microsoft Excel, Microsoft Outlook, anything. So operating system provides an interface between the application program and the user. So when you click on any application, this application is started. So this application, so it means say that so everything, let's assume when you start a program and operating system allocates some memory for the program. So does the user see this memory? My
No,
question.
sir.
Does not see. And if you look at a program, so what is a program? So actually, when the program are written in any high level language, like let's assume C, C++, any language, and then you have an executable file. When you click on that executable file, operating system will allocate the memory for program. But if you look at the program itself, so what does the program consist of? We have studied in assembly language. The program is divided into subroutines. Am I right or not?
Yes, sir.
And this subroutine consists of assembly level instruction. Am I right or not?
Yes, sir.
And who translates the?
एक्सक्यूज मी सर
बेटा?
सर इसके अंदर सब रूटीन का मतलब क्या है?
Subroutine, any subroutine, let's assume add subroutine, divide subroutine. If you think of a subroutine in C, C++, so let's assume a function, if you write a function, so the function is an equivalent of subroutine. So we call subroutine in assembly and we call it function in C. ठीक है बेटा?
ओके सर ठीक है.
Very good. Okay, now let's assume that who translate the program. So now let's assume you have a program. Okay, so I'm writing a blank box. So now let's assume this is a program. Okay, and this program, let's assume it is a C program. Okay, and there is a guy or there is a tool. They transform this C program into assembly level instruction and binary instruction. What is the name of that tool? What is the name of that tool?
A compiler maybe.
Compiler. Yes, very good. So the compiler transform a program that is written in a high level language. So there are different examples of high level language. It may be C, it may be many programs. So another program is C, C++. Maybe there is also a program that is a basic. So there is a compiler that transform this high level program into assembly language instruction. Okay, so what does what is the role of a compiler? So can I write it like this? What's a role of a compiler? So compiler provide an interface. Okay, now I have told you that the operating system provide an interface between the user and the application program. So can I write it like this? Compiler provides an interface between whom and whom? You beta.
Sir, high level language and low level language.
If we look at it if you think from the user perspective or something like that, so it provides an interface between the software programmer
and user.
Software program and the system. And the system. What is your system? System is your any processor. Maybe it is x86 processor or something like this processor system. So it provides an interface between the software programmer. Who is the software programmer? Any C, C++ programmer and the system. So software, who's the programmer? C, C++ programmer, C or C++. And the system, who is this? System under consideration is any x86 based system, core-to-do based system, core-to-do or any core. So it provides an interface between the software programmer and the system, and it transform the program that is written into the high level description into low level description. Okay, you got my point?
Yes, sir.
Okay. So now this behavioral domain, in a behavioral domain, is by the software programmer, and there are different levels of abstraction. Okay, now there are two levels of abstraction. Okay, one is the high level of abstraction and one is the lower level of abstraction. So if we say higher level of abstraction, so there are two things: higher level of abstraction and a lower level of abstraction. Higher level of abstraction and a lower level of abstraction. So at the higher level, details, and at the lower level, there are more. So the higher level of abstraction is more closer to the system user or the user, and the lower is more closer to the machine. So if we say any C, C++ program, it is at a high level of abstraction or lower level abstraction compared to the scenario when we write the same program in assembly.
Sir,
Higher level.
low level.
Assembly is lower level or high level?
Assembly is lower level.
Low level.
And any C, C++ program?
High level.
High level. High level. And at a high level, we have less levels of details, and at a very low level, we have more and more details. So now this is a genre of abstraction. So at the high level of abstraction, you have less detail, and at a lower level of abstraction, you have more details. Now we study another level of abstraction that we call as a structural domain. Can you see on the screen structural domain, Beta?
Yes, sir.
Okay. So now if you look at the structural domain, it is used by the system engineer. So if we look at the system at a very high level, so now it is we have a PC, okay, personal computer. The personal computer consists of monitor, CD-ROM, hard disk, and keyboard. So now if you look at the architectural extraction, so this PC we are only taking one component, it is a processor. Okay. And if you look at the processor, we studied already in embedded system. So what does the processor composed of? Processor consists of arithmetic logic unit, instruction fetch unit, instruction decode unit, and load store unit. So these are various components. We already studied these in embedded system. So we have a register file, and register operate on two different operands, and we sometimes we read the data from register, sometimes we read the data from the memory, and it is determined by the addressing mode. We already studied this in a system course. So if you look at the processor, so the processor consists of adder, divider, mux, register bank, and cache. And if you look at each individual components, so each individual components consist of gates. And if you look at the gates, each gate consists of multiple transistors. So if you are working at the processor level, so we are at a higher level of abstraction or lower level of abstraction? Ji beta.
The higher level.
Higher level. And what about this transistor level?
So low level.
Lower level of abstraction. And in Vlsi design, now I come to the Vlsi design, and if you look at the Vlsi design, so we will design a system at different level of abstraction. We will design a system at transistor level. We will design a system at the gate level. We will design a structure at the structure level, like at the adder level or divider level, and we will also design the system at a very high level of abstraction. And we will study these different level of abstraction in more and more detail in our upcoming lecture. Okay. So now we study with the physical domain. Physical domain, another level of abstraction in the physical domain, and it is used by the mechanical or electronic engineering. Okay. So if you look at the structural level,
सर सिस्टम इंजीनियर्स कौन होते हैं?
क्या कह रहे हैं?
सिस्टम इंजीनियर
कि सिस्टम इंजीनियर क्या की बात कर रहे हैं?
सर वो कौन से होते हैं?
System engineer is design the complete system. He's combining various components to realize a complete system, and he's putting different things together to complete to design the complete system. So he also he said, okay, he's designing it how different components of the system should be connected together to realize a complete system. Okay, you got my point or not?
Yes, sir.
Okay, so let's assume you have different components. You have different components. You have a processor. You have a memory. Okay, and now you're in a hard disk, and the system engineer is connecting all these components together to form a complete system. Maybe each of component is designed by separate design engineer. Separate design engineer. Maybe the processor is designed by one company, maybe the memory is designed by another company, maybe the hard disk is designed by another company. What the system engineer is doing, he's integrating all of these components and interconnect them together, and then he tests the system that whether the system is working correctly or not. Okay, beta?
Yes, sir.
Okay, now we now study another level of abstraction, that is the physical domain. It is used by mechanical and structural engineer. And if you look at the system from the physical perspective, so we have boxes. So now you have different boxes. Now let's assume you have CPU box, and if you look at internal into the CPU box, it consists of different boards, maybe PCB boards, and now you have hard disk slots and different slots. And if you look at the each individual PCB, so this PCB consists of different chips, and all these chips are connected together. And if you look at each individual chip, so this chip consists of I/O pins, Each chip has some IO pins. And if you look at each individual chip internally, so this chip consists of various mask layers. So in each of the chips, we have some transistor layer and we have some metallization layer. So actually, when you want to connect different transistors, so the transistors are connected through the metal layer. So it's just like a multi-story building. So the transistor layer consists of various layers, layer 1, layer 2, layer 3, and then we have metallization layer, layer 1, layer metal layer 1, metal layer 2, metal layer 3, and metal layer 4. So if you look at from this perspective, so if we are going into more and more detail at the transistor level and at the mask level, so actually there are more and more details at the lower level, and there are less and less details at the higher level. So if we think of the system as a box, so it is a high level of abstraction or lower level of abstraction? Give it a
Higher level.
Higher.
higher level. Okay. And if we look at the most lower level, okay, so the mask layers with a more lower level. Okay. So more details are at the lower level or more details are at the higher level?
Lower level.
Lower level.
Okay, so now you got the point. Now you got the point. What is an abstraction? Got the point, beta? What is the now? I have to ask a simple question. That what is the advantage of abstraction? G. Some question. G. Anybody?
डिजाइन प्रोसेस को सिंपल बनाने के लिए सर
Design process system and
Sir.
provide an interface. Provide an
Yeah.
interface between the user and the internal system, and to hide the details. To hide the details of the internal system from the user or the application programmer. Now let's assume if I'm writing a C++ program, and if I have to allocate the memory for the program myself, would it be easy for me to write a program, or it will be difficult to write a program?
Very difficult.
It will be difficult to write a program because I have to personally allocate a memory program. Who does this job for me? The operating system and also the compiler. So now let's assume if you are writing if you're writing any C code or C++ code integer a, what does the operating compiler does? So the compiler allocates a memory location for the variable a. You got my point or not?
Yes, sir.
Okay, if I'm writing like this, float array 10. What does the compiler do? What's the job? No, what will the compiler do?
सर ये 10 लोकेशंस दे देता है किसी
Compiler will
array
allocate 10 memory location for the floating point unit. All these details, are these visible to the program or hidden from the programmer?
not visible.
Not visible. It is hidden from the program. Which memory location? What is the address of that location? If you remember in the embedded system, how does we organize the memory? G. Memory has some address and data. If you remember or not,
Yes,
Yes,
sir.
sir.
yes sir.
you don't know which memory location will be allocated for the variable. And it's not the job of the programmer. It's the job of the compiler and the operating system. It's the job of the compiler and the operating system to do this memory allocation. Okay, you got my point?
Yes, sir.
Okay, so now we will study different digital designing of VLSI. Okay, we will do this in more and more detail or in our upcoming lecture, but I will just give you a very brief overview that how we can design a system at various level of abstraction. How we can design the same system at various level of abstraction. So now, designing at the behavioral level. Can you see on the left hand side?
Yes.
जी sir.
Okay, so what's a behavioral representation? So first I will define the behavioral representation. So behavioral representation describe how a particular design should respond to a given set of input. Okay. So behavioral description describe how a particular design should respond to a particular set of input. I will give a very simple example of a behavior. Okay. Now let's assume we have an adder. And it's a 4-bit adder. We have two inputs, A and B, and the output is, let's assume, sum. If I add 5 and 3, what will be the result?
8.
So now this is the behavioral description of an adder. You got my point or not? It's very simple.
Yes, sir.
Okay, now let's assume we have another behavioral description of a, let's assume, subtractor. We have a subtractor and we have the same set of inputs, 5 and 3. What will be the result?
2.
So now this is a behavioral description of a subtractor. So if we have an ATM, automatic teller machine, so what is the behavioral description of an ATM?
सर इनपुट कार्ड इनपुट करो और अपना पिन तो यू कैन हैव योर मनी या फिर जो भी आप करना चाह रहे हो
You can,
transactions.
at a very high level, you can perform various banking transactions through the ATM. Am I right or not?
Yes, sir.
Yes sir.
So this is a simple behavioral description, and it says that how a system should respond to a given set of inputs. So let's assume I give this input, the system will give me this output. So this is the simple behavioral description. Now, if you are designing at a behavioral level, and we are designing a system, digital system. So we are designing in VLSI design, we will be designing any digital system, and we will study different type of system, and we will design different type of system at various level of abstraction. But now, how we can design a system at a behavioral level? So now let's assume we have an example. Let's assume we want to design a 4-bit adder. We want to design a 4-bit adder. Okay, so if you look at a 4-bit adder, so actually can how this adder will look like? So now we have a black box. We have a,
It will have 4 inputs and 1 output.
so it means we have a black box. Now we have an adder. Let's assume the first input is a 30. So what does it mean? जी बेटा बताए ना?
Sir,
Significant bit.
जी बेटा बताए?
sir ये 30 बता दें थोड़ा सा.
Okay, I will explain it. No problem. I will explain it. I'm here for explaining. No problem. C in, and now you have C out. Actually, this is a compact representation. This is a compact representation. So if I'm writing, so I can write it like this. So A30 means, can I write it like this? I will write it here. I will write it here. A0 means we have a 4-bit signal which has A3, A2, These are the individual bits of the 4-bit signal, A1 and A. Better not.
Yes, sir.
Okay, so now let's assume I have any signal. Let's assume I have signal M, any signal M31 0. So what does it means?
Uh,
31
32 bit.
31 bits.
It's a 32-bit data, M31, M, T, and then M.
सर टोटल
39.
32 बिट्स होंगे ना?
Yes, here will total be 32 bits, M0. Which bit will be the most significant bit?
32nd M31.
Yes. So this is the MSB bit, and this one is the
लीस्ट सिग्नल एलएसपी.
बेटा समझ आ गई बेटा आप लोगों को?
जी सर, आ रही है.
Very good,
Yes.
very good. So now if we want to design this system at a very high level of abstraction, and if we have the look at the block diagram of this adder, so what are the possible inputs? So it means that now we have 2 inputs. So it's a 2-input adder or 3-input adder?
2 सर.
2 input.
So it's a 2-input adder. Very good. So what is the size of the input A? What is the size of input A?
4 bit.
4 bits.
4 bits. What is the size of input B?
Same.
4 बिट्स.
4 bits. And if you look at the output sum, what is the size of sum?
4 bits.
And similarly, C in is a single bit and C out is a single bit. Okay.
Yes.
ओके.
Okay. Now, if you look at the if you look at the system, and if you look at the system, and there is a very long code on the left hand side. Can you see the code?
सर ये सी इन और सी आउट क्या चीज है?
Carry in and carry out. I think so. You have studied this for 4-bit adder and triple carry adder in your digital logic design.
Yes, sir.
If you remember.
लेकिन वो confuse हो गया ना. C++ में भी पता C in C out करता है.
No. This is not. We are not studying any C++. We are only studying the. You can also call it carry in and carry out, right?
यस सर.
Okay. Okay. So now let's assume if you want to write any code, very long code for it. Okay. So I'm writing any code for it. Okay. So maybe I will explain this code in more and more detail later on. But if you look at the system, so first we have to write the code. So actually module. I will start with the module. Module is a keyword. I will explain it later. How does a module work? So what's the adder? With adder. And what are the and then you have to write in module. So what are the interfaces in this black box? What are the interfaces?
A, B, C,
A, B,
C out,
C in,
sum.
and C out. So actually, if you can you write it like this? I can say A, comma B, comma C in, comma sum, comma C out. So these are the interfaces. So when you have to write any code, so module is the name, is a keyword. You have to use this module. 4-bit adder, you can give any name. You can give any name. For instance, Gulbaz Khan, if one of your colleague, you can give any name to this module. And you have to write the interfaces. What are the inputs? So if you look at the A, B, C in, so if you look at A, B, C in, so A, B, C in are the inputs or the outputs?
Inputs.
And what are the outputs?
Sum and C out.
The outputs. Okay, now actually what is the size of the adder? What is the size of the adder in our case?
4 bit.
4 bit. So it is input or output?
All of them are
In-
both inputs and
It's a 4 bit, so it means input 30 AB. So A and B are both in 3 bit input. Any problem?
no.
Okay. And now what about C in? It has a 1 bit signal, so we can directly write it. So whenever do not mention the size, so it's a 1 bit signal. So input 1. Okay. What about? Okay. What about the sum? How can we write for the sum?
Output 3
Output, very
for
good.
0.
Very good. Output 3.0
And
sum.
sum.
What about Cout? Cout is a 1 bit signal or
1
multi-bit
bit.
signal?
Out.
1 bit.
Output. Cout. Okay. So this is the now we have defined our system, and we have defined the interfaces of our system. And this system is a 4 bit adder. So this 4 bit adder is our system. Okay. And any designer can interface this system through its interfaces. And what is the interfaces? A, B, C, in, sum, and out. So these are the interfaces. These are the interfaces to the system, and now it is a system. And this is a very simple code. Assign C out, comma sum to A plus B plus C in. Okay, I will not explain this code at how this code will work, but actually whenever I write this code, it will design a 4 bit adder. Whenever I write this code, it will design a 4 bit adder. Can you see any gates here?
No, sir.
Okay. So who will transform this? Actually, if we implement this design or system on a chip, so actually if you look at any system or any adder, so what does adder consist of? Am I right or not?
Gates. Yes, gates.
And gates consist of transistors. Am I right or not?
Yes, sir.
Okay, so actually you may have studied in digital logic design that let's assume you may have designed a different type of adder. What's the type of adder that you design in digital logic design? What's the name of that
Half
adder?
full ladder.
Half adder and full adder, if you remember that. And actually, if you want to design a 4-bit adder, what's the approach that you use in your digital logic design?
मल्टीपल अगर हम 2 बिट्स एड्रेस यूज करें तो उससे भी हम डिजाइन कर सकते हैं
Yes, so actually you cascade different adders in a cascaded fashion. Am I right or not?
Yes, sir.
यस सर
Where the C out of one adder is the C input of the next adder stage.
यस सर
Am I right or not? And if you
Right.
look
Right, sir.
huh? जी बेटा जी बेटा हेलो
सर मैंने कहा राइट सर.
Okay, very good. ठीक है. अच्छा, if you look at that adder consists of gates. So if you look at one bit adder, so actually if you remember this 1 bit adder is actually something like this. Let's assume we have a 1 bit adder. So let's assume this is a 1 bit adder. So actually the input to this 1 bit adder is we have 1 bit A, B, and C in, and the output is sum and C out. This is the carry. Am I right or not?
Yes, sir. Yes.
Okay. Now, how we can calculate the sum? How we can calculate the sum at the gate level? Is it, am I right or not? If we can, maybe you have designed this adder like this.
Yes, sir. गेट्स यूज किए थे अब से याद नहीं है लेकिन ऐसा ही था.
So now this is only the expression for sum. I'm not looking for C out. What's the expression for C out? But this is the expression for sum. How many gates are used to realize sum? How many gates? Two gates. So now this gate G1 and then this gate G2 is realized for the sum. And it is only for one bit. If you have multiple bit adders, so you can connect them in a cascaded fashion. Okay?
Yes.
Now, now if we see that, okay, now it consists of gates. Can you see any gates in this code that I have written?
No.
So actually this is designing, we are now designing at a higher level of abstraction and we are using a plus operator. So whenever we will use a plus operator, what will be synthesized?
And give.
Adder. And if you use a minus sign?
Subtractor.
Subtract. So now, what we are designing at a high level of abstraction or low level of abstraction?
High level.
High level. Which sign did we use here? This plus and plus. Okay, now I have another question. Now, who is responsible? Okay, now I'm writing it. Okay, writing here. Who is responsible to convert the design at higher level of abstraction अच्छा, which type of abstraction is this? कौन सा domain है?
High level.
Behavioral domain, if you remember or not.
Yes, sir. Behavior.
Who is responsible to convert the design at a higher level of abstraction from the behavioral domain to gates and then to transistors?
Sir, first compiler, then OS.
Now we will not use a compiler. Compiler is only used for application program written in C++. This is not C++. This is
Then
very
the
long.
process.
No. So there is a tool. There is a tool that transform the design at a high level of description, that is the behavioral description, into transistors. And what is the name of that tool? So maybe you don't know this, the name of this tool. We call this tool as a logic synthesizer. Logic? So what is the job of logic synthesizer? Logic synthesizer transform a design at behavioral description into transistor and gate. Okay, you got my point or not?
Yes, sir.
समझ आ गई बेटा?
जी.
Okay, so now, so the job of the logic synthesizer is to transform a design that is described at the behavioral description into transistor and the gate level. So now, this is a behavioral description of any ATM, a very simple behavioral description of an ATM. So, if you look at this system, an ATM or any auto teller machine, not the bank ATM, it's a very simple machine. So when you insert a coin, into the machine or any node insert, it will give you a Coke. So what is the simple behavioral description of this ATM? Can you see on the left hand side in the green?
Yes.
जी सर.
Yes.
Okay, so the system is expecting some input and it is expecting some coins. Okay, so if the coin is inserted, so it will give the coke, and if the coin is not inserted, it will again go to the initial state, and initial state it is expecting some input, and it is continuously monitoring that input. It's a very simple system. So this is the behavioral description of an ASM. It is expecting some input, and we have represented the system in the very small flow chart. It's a very simple flow chart of it. But if you look at the block diagram of this system, so what are the block diagram? What is the block diagram? What is the input?
Coin.
Coin. So if the coin is
And
inserted, insert a logical one. And a clock and a reset. The system will operate on a clock, and because it's a finite state machine, and we will study this in more and more detail in our upcoming lecture. But at a very high level abstraction, the system will run on a clock, and let's assume your process is running on a clock, and it perform various operation at different clock instance. And a reset. And give coke is the signal that is asserted by the a total teller machine. When give coke is 1, it means it will give the coke to the user. Okay. So now this is a very simple behavioral description of an ATM. Did you got my point or not?
yes, I got it.
Yes sir.
Any questions?
Yes.
Any question?
सर इसमें एंड गेट यूज हो सकता है
इसमें
इसके अगर हम डिजाइन में देखें तो कॉइन और क्लॉक का अगर
yes. Then
and
how does this design will be realized? I'm not going to detail into this design because this design is a little bit more complex, and we will study this more and more detail in our later lectures.
okay.
But I just want to give you an overview that how you can have an overview of the what's the behavioral description of an ASM in terms of the flow chart.
Okay, sir,
Okay.
got it.
Now let's assume we have designed this adder and we have synthesized this. We have designed this adder in a 4-bit adder. Okay. And what is a function verification? Function verification and testing. So the behavioral in the functional verification, we test our system by giving a given set of, and we check the outputs, and then we see that whether our design is correct or incorrect. Okay. So we are giving different inputs at different time instants. So if you look at this timeline, this is the timeline, and we are different time points. This is okay. So there are different time points. This is time 5. This is time 10. This one is time 15. Can you see the timeline, beta, on the left hand side?
Yes, sir.
This is the timeline, and we are giving different inputs at different time. So at time t0, the first input A is 5, the second input B is 4. So what will be the output from the system?
9.
So this is 9. So this is the sum. So in the functional testing and verification, we give a particular set of input, and then we expect some output. And in functional verification, we test that whether our design is working correctly or incorrectly. Am I right or not?
Right, sir.
Okay. So now let's assume that if in the adder block, instead of assign cout sum, I have written this. Let's assume I have written this: assign cout is equal to A minus B minus C in. And I synthesize the system, and if I test the system, will it give me a correct output or incorrect output? Anybody? बेटा आवाज नहीं आ रही?
करेक्ट ही देगा क्योंकि माइनस साइन को वो एज अ सब्ट्रैक्टर लेगा ना, अभी थोड़ी देर
तो
पहले
सब्ट्रैक्टर
हमने
लेगा, but we want to design an adder.
अच्छा हाँ फिर तो गलत होगा।
गलत होगा ना, because actually the problem is, the point is like this: being as a designer, you are writing a code like C++ code, and you want to add, and instead of add you have wrongly like this. So this is a logical error or syntax error?
लॉजिकल एरर है।
It's a logical error. But how do you test your system then? How do you test your system?
उसको सारी कंडीशन से गुजार के एक दफा देख ले।
Yes. So you give different set of inputs and see that whether your design is correct or not. So now let's assume if you want to test your system, you give different inputs. You give 5 and 4 at time 0, and you get 9. You say, oh, your system is working. Then you add 2 and 3, and you say 5, and then you say, oh, now my adder is working fine and correctly, and then now I can proceed further with this design. Okay.
Yes, sir.
So this type of simulation is called as functional simulation. Okay. So in a functional simulation, we see that whether a design responds correctly to a given set of input or not. Okay.
Okay.
Okay. So what is the now we are studying the advantage of designing at the behavioral level. So what is the advantage of designing at the behavioral level? So it reduces the time to market. Yes, because when you are working at a very high level of abstraction, it reduces the time. You want to design an adder, and you design an adder just with 3 very simple step: A plus B plus C in, and you have designed an adder. Okay. So it reduces the time to market, and it actually you write a code more in very small time. So now let's assume if you want to write a code in C, or if you want to write the same code in assembly, which one is easy?
C.
In C. So which will reduce the time to market? Design at C level or assembly level?
At C level.
At C level. So now similarly, if you are designing at the behavioral level, and if you are designing at the transistor level, so which one will be more easy? Behavioral level or transistor level?
Behavioral level.
Behavioral level. So which tool is transforming your design at the behavioral level into transistor and the gate level?
Logic synthesizer.
Logic synthesizer. So actually, if we say logic synthesis, now this is the logic synthesis converts the behavioral description into gate and then into transistor, and it relieves the designer to design at the lower level, and it improves the productivity because you are designing much faster. Okay. And it is architecture independent. You don't know that which architecture you are using, whether you are using FPGAs or VLSI. We will discuss this in more and more detail. So let's assume if you write in C code, so you don't know the architecture. Which processor are you using? Any processor. You can use any processor and it will transform into this. So you don't know the details of the system. Okay, beta?
Yes, sir.